Hello and welcome. The purpose of this video is to help you out with problem 7 from the Unit 6 assessment. So problem 7 was where we got probably the most number of questions and the most amount of concerns. I wanted to really make sure that I'd walked you through this and you were feeling good about problem 7 moving forward. All right, so let's take a look at the problem. My first step whenever I do any problem is always to read the problem out loud. So, Ms. Joseph and Mr. Swanson both join her being Miss Miller, on this exciting adventure. What a fun adventure land and imagination land we are living in. Miss Joseph indeed does not like parachuting, but we can pretend. Both Miss Joseph and Mr. Swanson's parachutes were built a little differently from Miss Miller's parachute and allowed them each to travel at a constant velocity of 7 meters per second. So that tells me that for all of these problems in number 7, V for Ms. Joseph will be 7 meters per second, and V for Mr. Swanson will be 7 meters per second. All right, great. So Mr. Swanson is asked to pull his parachute when he was 900 meters above the ground. How much time should he expect to be falling with his parachute open until he lands on the ground? I like to draw a little picture for myself so that I can tell exactly what the problem is asking me. So here's Mr. Swanson. He's pulled his parachute. He pulled his parachute 900 meters from the ground. He's still falling, and we're wondering how much time he's going to expect to be falling. So my givens, my velocity is 7 meters per second. My displacement is 900 meters. Notice that in this case, we're considering displacement as above the ground. That's how we're setting up problem A. And what I want is time in seconds, the SI unit. Of course, S equals VT, that's the only equation we learned, so that's the equation we're going with. Okay, so we have 900 meters equals 7 meters per second times time. We're going to divide by 7 meters per second, and our time will be equal to 900 divided by 7, 128.57 seconds, which you could also round up to 128.6 seconds. Either way, we accept it. Either way is great. Okay, part B. So Ms. Joseph jumps from the plane and falls 1720 meters before pulling her parachute. So here's my plane. Miss Joseph has fallen. Here she is. And let me draw the parachute a little bit better. So here she is. She's going to pull her parachute. So she's gone 1,720 meters. She pulls her parachute, and then once she has her parachute, it takes her 210 seconds to hit the ground. How far did she fall in total? So now our displacement is the total displacement. And so Ms. Joseph has traveled from the plane to the ground. So what is the total displacement? So my initial displacement is 1720 meters. I want my total displacement. In order to find that, I'm going to have to find the displacement after the parachute. And my time, I'm going to use the 210 because I need to put it in SI units. And my velocity from before was 7.77 exactly meters per second. All right, S equals VT. That's still what we're working with. So I'm going to solve for only after the parachute. I'm going to find this distance here. So I know it took 210 seconds. I'm trying to find this distance. S equals 7 meters per second times 210 seconds. 7 times 210 gives me 1,470 meters. And then I need to add that to my initial displacement to get the total. So plus 1720 meters, so equals 3,190 meters. So the key here was recognizing that the only thing you needed to calculate was after the parachute, and then go back in later and add in that displacement that they'd already given you, that she'd already fallen. Okay, so 7A and B were both answered pretty well. 7C was where people started having some issues. So it turns out that while Ms. Joseph is falling, Ms. Miller is also falling. Ms. Joseph wonders when she will catch up to Ms. Miller, who is currently 130 meters below her. All right, so I'm going to draw this situation, even though we do have a picture here. So here's Ms. Joseph. Here's Ms. Miller. At some point, they're going to catch each other. So I'll put her up a little bit just to give myself some space. That's crazy hair, but they do also have parachutes. So here's Miss Miller. They're both falling, and at some point, they're going to catch each other. What do we know about their falls? Well, Miss Joseph is still going 7 meters per second, like before. Miss Miller, you calculated her velocity in part 2 from the graph. So Ms. Miller in this case has all different velocities. Let's just use the velocity from version A. So maybe Miss Miller was going 3.6 meters per second. This number varied based on which version you have that you found from your graph, from your data. Okay, so Ms. Joseph is going to fall some amount until the two teachers catch each other. Ms. Miller is also going to fall some amount until the two teachers catch each other. We don't know what those two distances are, but what we do know is we know that this distance, this initial difference in displacement, is 130 meters. All right, so I'm going to call this distance that Miss Joseph needs to fall x, because we don't know what it is. What does that make this distance that Miss Miller is going to fall? Well, x minus 130, because this total area is x, and then we start off with 130 meter difference between the two. All right, so what are our givens? We have velocity for Miss Miller is, in my example, 3.6 meters per second. Again, this varied. And my displacement for Miss Miller is x minus 130. Joseph's velocity, Miss Joseph, is 7 meters per second. Her displacement is just x. And then we don't know anything about the time, but we do know that the time for Miss Joseph is equal to the time for Miss Miller. What do I want? Well, I want to know how far Miss Joseph goes. So I want to know S for Miss Joseph. S equals VT. We're going to need to use this equation twice, both for Miller and for Joseph. All right, so let's start with Joseph. S equals VT. Well, I just said that S was X. I said that right here. Equals 7 times time. And Miller, again, S equals VT. I just said that her S was X minus 130 equals her velocity times time. All right, so notice I have 7t is equal to x, so I can actually just plug in. I know x is equal to 7t, so where I have an x in Miss Miller's equation, I can just plug in and do 7t minus 130 equals 3.6t. All right, and now at this point, I need to solve for t. So I just have an algebra problem. I'm going to do 130 equals 3.6. I'm going to subtract 7t from both sides. 7t, 3.6 minus 7, that gives me negative 3.4t. T is equal to 38.235 seconds. Okay, and now remember I was looking for velocity of Miss Joseph, so now I need to solve for that. I can plug this t back in to one of the equations, and this is not negative, this is 3.235 seconds. And so now if I go back up here to S equals VT for Joseph, S equals 7 times 3, 38.235 seconds. And so that's going to be equal to 267.6 meters. All right, looking at the graph, notice you do need to label what's going on. So let's say that Miss Joseph is starting here. If Miss Miller starts here, well, I know that this needs to be at 130 meters. And I know that they're going to hit each other. I just calculated at 38.235 seconds. So they're going to collide here. So notice these lines have two different slopes because Miss Miller and Miss Joseph have two different velocities. Miss Joseph's velocity is faster, and so that's why her slope is steeper. And now, when they collide, they start going at the same velocity, and it's steeper than both of these initial velocities. So in 3, you should explain how you got the y-intercepts, the slopes, and post-collision. All right, I hope that helped. Let us know what questions you have. Have a good day.